last speaker of this morning is from our own Radboud University. It's an organizer of this workshop, Wolters, and he will be giving a talk about Neorealism and the internal language of topoi.
Where it said Radboud, was that addressed to us?
Sorry?
It said on the board Radboud, but it's gone away now.
Not just the thing. Well, first of all, I would like to thank myself for this opportunity to stand here and talk. It's a bit awkward to do so. I mean, it's kind of like liking your own Facebook status or high-fiving yourself to give a talk on your own workshop. But thankfully, it's a short talk, and looking at the subject gives a good handicap. Because the material that I would like to talk about is of a technical nature. It has a conceptual motivation, but it is quite technical. As we will be thinking about working with inner and outer designation of self-adjoint operators on the one hand, and also be playing with the internal language of the contravariant topos on the other. So, just to get an idea of the basic picture here, what I will try to do here is one thing I'm always wondering is in how far is the internal language of this topos. So I will be concentrating on the contravariant case. So this is the pose set of von Neumann subalgebras. I will denote it by C. It's not customary, but I can denote it by VNU, but at some points I will make mistakes and move over to C.
So if you turn the light switch and rotate this to increase the number of photons on the blackboard, then you have a better view.
So I have this pose set of abelian von Neumann algebras, opposites, and we take the presheafs from this guy to sets. That's the base topos in which I'm working today. And the various constructions of this contravariant approach, I would like to see if they have an internal description, if I can find some topos internal description which is natural from the point of view of this idea of neorealism, as sketched, for example, in the first few sections of that massive paper, What is a Thing? And I think it's best to just start with one of the central players of this approach, the Spectral Precis. So there's no need to define this guy. We've seen it time and time again. And well, in the previous talk it was called a spectral object because it's an object in this set, and in this, well, topos, in this category of sets in some generalized sense. But we think of this guy as being like the state space of classical physics. We would like to think of it as being something as a space. Well, working with von Neumann algebras, I'd say something like a measure space, but I'm not that handy with measure theory inside topoi, so I'm going to play safe and I will look at it like a topological space inside this topos. Before I make this precise, I should first need some tricks. The first one was already mentioned today. This category is equivalent to the category of sheaves on C with the, you call it co-Alexandrov or anti-Alexandrov topology. So I give this the topology where a subset or a set of contacts is called open if for every context which is in it, every coarser context is also in this subset. It's downwards closed. So that gives a nice topology on C, and these two topoi are equivalent. I would like to see this as a sheaf topoi, because then I can turn to chapter 2 of McLean and Moodek, Sheaves in Geometry of Logic, which tells me that the category of sheaves on a topological space is equivalent to the category of étale bundles over that space. So associated to this guy, there is a bundle over this space. I will call it pi. As a set, this guy is just the disjoint union of all Gelfand spectra of these contexts. And I will not discuss the étale topology on it. It's easy to find an explicit form for that, but I won't need it for what I'm talking about today. So, yeah, this guy can be described as a bundle. Now I like to turn my attention to a nice old paper by Ike Moodek. It's called Spaced Spaces, I believe, and that deals with the notion of topological spaces inside a topos. So in the internal language, just to be clear, when I say internal, I just think of objects as sets, arrows as functions, and using the Mitchell-Benabou language, we can interpret all kinds of structures in this topos, and we can prove stuff about that, just like normal set theory, using the semantics, with some important differences with normal set theory, in the sense that we have to work with generalized elements, which, looking at spectral presheaf, seems like a natural move. Spectral presheaf in combination with Cauchy-Specker theorem. And we also have to we have to avoid stuff like axiom of choice and law of excluded middle. All rules of intuitionistic predicate calculus all hold in any topos, but as for the other two, you can only assume them without running into contradictions for special topoi. So for sets you can assume them without getting into trouble for this guy, unless you're looking at something really uninteresting like the complex numbers for your operator algebra. In almost every other case, I'd say law of excluded middle does not hold, and only weaker versions of the axiom of choice, axiom of dependent and countable choice, still hold. And these, by the way, fail for sheaf topoi. So just to get clear what I mean by working internally, and Mitchell-Benabou language, Crépy-Jugel semantics. So, so in this paper, Spaced Spaces by Ike, the notion of a topological space in a topos is defined exactly how you would expect. Suppose we have some set in a topos, in our case the spectral presheaf, then a topology on it is a collection of subsets, subobjects, such that the internally written down, the empty set is in this collection, the whole set is in this collection, it's closed on the finite intersection, an arbitrary union. So that's what it means internally. It's just exactly what you expect. Externally, it has a nice description in terms of this bundle. For one thing, any sub-object of this presheaf corresponds exactly to an étale open here. There's just a correspondence between the étale opens here, sub-objects here. Defining a topology on this internal guy amounts to giving a new topology on this space, which is coarser than the étale topology, and this function is still continuous with respect to this new topology. So I'd say this would still be an op vibration, right? Or is that not that easy to see?
What's getting in my way is I'm not quite sure the relation between modic spaced spaces and the point-free spaces that we talk about.
Okay.
But you've got your bundle, haven't
Yeah,
you?
you got your bundle, and thinking of it as a point-free space just says that we forget that it comes from a cosine topology and then the étale topology. So if you just ignore the first étale part and you're just working with a locale.
I agree, it does look like an optimization, doesn't it? Which sounds wrong.
I'm not sure if it sounds wrong. It sounds right in the sense that the natural topology to consider here is to take the often mentioned closed-open sub-objects of the spectral precis. These play a very important role here. So these form a basis, these are a basis for an internal topology. And I will take the topology on this guy to be the topology generated by the closed open sub-objects. So is this clear? Okay. So that's basically how I will look at the spectral precis. I will mostly work in a bundle picture because I want to work internally and I want to work continuously. And then it's, yeah, the bundle picture is just really useful. Keeps things simple. So yeah, that's the way I will look at this spectral precis as an internal topological space. So aside from this space object, we also need in this formalism of this idea of neorealism, you also have value objects. I also would like to think of these as a space of values, and for that I consider there are two natural candidates of value objects to consider in this approach. First I'm going back to the topos of sets right now. I'm going to define two kinds of real numbers, the upper real numbers, the lower real numbers, which in the classical topos of sets define exactly the same set. But they also have a natural topology. As topological spaces they are different. And then I'm going to consider the upper and lower real numbers as spaces and as sets in this topos. And I will use their product as my value object, as my space of values. So the lower real numbers in sets RL. Well, this is just, this is still general. So this works for any Grothendieck topos. I need a natural number object, but that's about it. So at least for every Grothendieck topos this will work. So a lower real is a subset of the rationals which is downclosed and rounded. By downclosed I will mean the following. Suppose that Q is an element of this, the rational Q is in there, and A is a smaller guy, then A should also be in there. And if Q is an element in here, then the set being rounded means that there exists some A which is larger than Q, and A is also in there. Well, classically, I'd say taking such a lower real just means either we have the empty set or the whole of Q, or if we identify this guy with its supremum of the Q's in it, we just have a real number. So as a set, it just corresponds to the extended real numbers, the real numbers that you're used to, with a minus infinity corresponding to the empty set and a plus infinity corresponding to Q. In addition to this, we also have a set of upper reals, and yeah, these are defined in an analogous fashion. These are up closed and rounded, and there here rounded means that if we have an element in there, then there is some smaller element also in this collection, so the order reverses there.
Simon, can I just say something about the classical view? Although the points are the same as the extended reals, you do see a difference in the topology, because this is a geometric presentation. There's a natural topology that comes out of that. In fact, it's the Scott topology and not the usual Haskell topology. So that is a way even a classical mathematician could.
And that was exactly what I was going for right now.
Oh, okay.
What we're going for right now. I want to look at them as locales, so I can't avoid the topology. I mean, the topology is the most important feature actually. The natural topology on the lower reals, if I identify these guys with the extended real numbers as we used to, I say the natural topology to consider on this guy is the topology generated by sets of this form, upper half intervals. Oh, sorry,
Yeah.
not close, definitely not close.
But close at the top, it allows infinity.
Yeah, good point. So this is the natural topology, and by natural topology I mean we're talking about propositional geometric theories here, and yeah, this is just the set of standard models of the theory, and just like for a Boolean algebra you have for classical propositional logic associated to a classical propositional theory, you can associate to that a Lindenbaum algebra. Likewise, for any geometric propositional theory, you have an associated frame, and this frame is the topology on the lower real numbers here, being the frame generated by these basics. But I want to emphasize these basics here, these are important. And likewise for the upper reals, we take the other intervals, the other half intervals. Now, it makes sense to talk about upper and lower reals in any Grothendieck topos. And right now I need a trick which, well, it's not really a trick, it's an important point which was also used in the previous talk, in that the categories of locales in the topos of sheaves over this guy is equivalent to the category of locales in sets over this space. So if I want to find a locale in this topos being equivalent to this guy, then I can describe it as a bundle over this guy. And for the lower real numbers in this topos, the bundle is of a simple form. This is discussed in great extent in I think, near the end of the elephant, the Bible of toposophy. Let's see, we take the product of this co-Alexandrov space with the lower reals in sets, and I project it simply onto the first coordinate. And this is the, well, bundle description of the lower reals in this topos. And just like here we have this space, here we have this space, but we also can think of it as the set of points. The models of the geometric theory. The associated points of this bundle are familiar, presheaf here. We've seen them yesterday at least once. So translating back to the original topos, This is simply the functor associating to every context the set of order reversing functions from the down set, from down C, every context coordinate C to the usual real numbers in sets. For the upper reals we have roughly the same. We take the upper reals, here, and here we get order preserving functions instead of order reserving functions. By the way, if you can also define Dedekind reals in your topos, and these would then be constant functions. So the Dedekind reals do not look that interesting, at least from the point of view of Designation.
But the order reversing functions of the imperial approach do not play a role here, or?
Sorry?
So you have either order preserving functions
And
or
order reversing functions.
that's what you said. I may have missed the P. Do you work with order pre or order reversing functions?
Order reversing functions in case whenever I'm working with lower reals, and order preserving functions whenever I'm working with upper reals. At least in this topos. And if you want to go covariant, then you need to reverse the two.
But also then you use both.
Yeah.
Okay.
Yeah, everything that I say here works well. Everything what I will say from now on also works covariantly just as much, but time restrictions make me choose one approach instead of doing both at the same time. Now I want to, I want to go to Designation. This morning we've already seen Designation of Projections, both outer and inner, but this can be extended to self-adjoint operators, and yeah, it's too complicated to discuss this quickly, but so that's suppose A is a physical quantity represented by, in the normal quantum formalism, by a self-adjoint operator of your operator algebra under discussion and phenomenon algebra, I'm assuming here. Then, for any context C, we can find approximations of A relative to C, by approximations of A by self-adjoint elements in this context C, such that A is in between them. But the problem, the order that I'm using here is the so-called spectral order, which is a very nice and interesting order to look at in this approach. But yeah, well, in both co and contravariant, I'm quite fond of the spectral order, but explaining that will take too much time. So for every context, out and inner designation gives a best approximation from below or above by a local self-adjoint operator. Now, what I like about these inner and outer designizations is the following. I can define an outer designization map globally from the spectral bundle, so equipped with this topology of closed open subobjects, to the bundle of lower reals, and then this commutes. So I take an element here. So this was the disjoint union of all the Gelfand spectra. So taking an element here is just taking a context and an element of the spectrum, and we map that to the same context and the pairing of this character lambda with the outer designization of A relative to this context. So we just pair this operator C with this character. And this is, of course, a well-defined commuting triangle, and it's also continuous. That's nice. And if I take the inner designation here, and I have to take the upper rails here, then I also get a nice continuous map. So again, looking at this equivalence of categories, what I'm doing here is defining continuous maps between these two spaces, internal spaces internally. I'm working internally here, but it just is simpler to write this down in terms of these bundles.
I haven't understood where you got the angle brackets and then the lambda.
Oh,
I haven't understood how you're getting a
so this is an operator in the context C, and this is an element of the Galvan spectrum of C. So,
okay, right.
but because we can look at this in different ways, we can also see it as the Galvan dual of this guy taking values in lambda.
Right.
They
So it's exactly the classical.
yeah, exactly.
State space.
Exactly. So we have these two nice continuous maps, and we can take them together, of course, and get a continuous map. Call this delta A from the product of the two. Actually, it's just up to isomorphism, the 5-bit product. So topos internally, I am taking the product of the upper and lower rails, and we get a nice continuous map here. So C lambda is mapped to C, this guy, and also the one for the outer designation. This is a nice continuous map, and one thing which has really been bugging me is the following. In the contravariant version, also covariant, but in the contravariant version you have these elementary propositions defined by so we start out with an open or Borel subset of the real numbers just in sets, and a self-adjoint operator, and by designation, outer designation of self-adjoint of projections, to this pair one associates a closed open subobject of the spectral presheaf. In other words, an open of this space. And what I would like, that's appealing from the internal perspective, is that if I pick a good open here, then the inverse image, associate to this delta a nice open here, then the inverse image of this continuous function should take that to the elementary proposition. And yeah, to some extent that works in a very nice way. So what I found was the following result, and I have no idea how much I think I will close after that result. What I found was the following. So let delta have a simple form, being an open interval from x to y in the real numbers. And associated to this interval, I define the following open here. I take the whole down C times upper rails. Now I need to have lower intervals, so minus infinity through y times x plus infinity. I will call this, I will denote this guy in this way, just to distinguish it from this open. And what I know is that for every epsilon greater than 0, if I take the inverse image of this web, let it act on this open, then what I get is the intersection of two elementary opens of this kind, so a smaller than y intersected with a bigger than x, and this again is a subset of the inverse image of x of any slightly larger interval. So just extend it by any epsilon, then I know that this is in there for sure. And in the case that x and y are not elements of the spectrum of A, then we can just ignore this epsilon babble and have an equality here. So I thought it was nice. We would like to have a connection, but it's not exactly the same as having this elementary proposition. It's mentioned a few times that outer designation of projection does not respect the means of the projections. Outer designation of projection does not respect these means. So this guy may be a lot smaller than this intersection. But still, I thought this was nice, and for me it increases the hope of getting guys like this back from as inverse images, though you have to look at more creative opens here. So there seems to be a nice connection between these elementary proposition and inverse images of these physical quantities represented as continuous functions from the spectral presheaf seen as a space to either lower real numbers, lower upper real numbers. So yeah, that's the important stuff that I wanted to say. So I'll leave it at that.
Are there questions?
Yeah, how do you think you do inner designation of the projections?
Oh, for inner designation, that's what inspired this. For my comparison paper, I looked at inner designation because this inverse image stuff, that's usually how they take the inverse image of continuous maps. That's usually how one does it covariantly, and I wanted to see if that fits nice with something which is closer to the contravariant version. So I used the inner designation of projections, and there you'll get the same result, and then you can just write either one of these two. These are the same there, because in that approach it's the disjunctions that are not respected.
So first of all, it's very nice, and I'm really interested to see this written up. It's really nice to show it to the world. On this last point, in some sense, conceptually, it's not surprising that it will be more difficult then, because what do? We have some external interval from x to y.
Mm-hmm.
We talk about an elementary proposition. Some physical quantity A takes a value in this open interval. Now we translate this into internal structures. And in particular, at this point, we do accept by using normalization that you cannot talk about A in all contexts. We have to coarse grain A. That is what normalization does.
Mm-hmm.
But conceptually, this implies you also have to coarse grain your proposition, your external proposition. A takes a value in x, y. It doesn't have a direct translation into the topos. You have to approximate, and this means also you will have to make the interval bigger if you go to smaller stages in general. This is why you have to look at more sophisticated internal opens to match this thing. There will be no perfect match from this external proposition to the internal thing.
Oh yeah, I agree. I see this as exactly a nice way to
Yeah.
study this internal and external connection between the values.
I totally agree. So I would actually put this in a positive way, that this shows.
Well, if I have sounded negative, then it will give them the wrong impression, because I'm happy with this, and
Okay, good, good. Yeah,
I
I'm
think
too.
this is.
So when you defined your sigma bundled over C, you were going to some lengths to explain how those were just going to be the spaces, so possibly non-sober.
Yes.
So
mostly not. I'm working over non-sober spaces.
So when you use the Joule-Cherney results, then your C would actually be the we're thinking of imperial approach here actually. So it would be the filter completion of C, and you'd get a corresponding thing for your sigma that would be a bit more than the sigma you wrote down.
That the imperial sigma gives me contravariant sigma.
Oh, you
looked
were
on
using
soberness.
stuff to put topology on as well,
Sorry?
aren't you?
I tried to look at this, so replacing this with the filters with the Scott topology,
Yeah.
and look at the corresponding bundle here, but that's going very slow. That's I find that technically a bit complicated to do it completely sober and pointwise. It tends to give me a headache.
Okay, so there's always a question: what happens if you try and fill in those extra ideal points, the filters? But you're not sure, and I can't see it in my own mind because I don't see how it's going to interact with the spaces.
Well, I would be very much interested in getting that part right. I mean, it's something I have been playing with, but it's a bit complicated. At least for me, I'm not used to spaces that look like that. But it would be good to see that.
Shall
The
we
extra
use
points.
the lunch for more questions? Let's thank Sander again.
And the lunch will be downstairs, on the floor.
Can we leave coats and things here? Can we leave coats and things here?
I can see the
No, typically not.